Our next speaker is Dr. Subhrajit Mukherjee from Technion-Israel Institute of Technology, and he is a postdoc fellow in Technion right now, and he received his PhD from the India Institute of Technology, and prior he in the master degree in 2013. And his research currently involved in the wide variety of micro and nanoscale device fabrication processes using two-dimensional ferroelectric materials for optically controlled integrated memory devices. And the title of his talk today is Electronic Properties of Two-Dimensional Ferroelectric Layer-Based FETs Using c-afm. Okay, welcome, Dr. Mukherjee. And you can start to share your PPT and give the talk.
Thank you, Faye, for the nice introduction. So today I am going to talk about how we can evaluate the electronic properties of the 2D ferroelectric materials or the 2D ferroelectric based heterojunction using the Kelvin probe force microscopy. So here is the outline of my presentation. First, I will in little bit introduced about the topic like what is the 2D ferroelectrics and what is the current status using the 2D ferroelectric based devices for this optically controlled memory devices, and what the material we are using for this purpose and why we are using this. Then I will show some experimental results based on the heterojunctions in form of planar and particle heterojunctions form and their characteristics using the Kelvin probe force microscopy. So Professor Lanja gave a nice introductions about the memory devices. So it's very nice for me to start from this point. So now we know like what is the memory devices based on the 2-terminal or 3-terminal devices. Mostly these memory devices are electronically controlled, like input and output are all electronic signals. And we know like in the early 2000s, there is a happy scaling era in terms of the Moore's law, in terms for the device miniaturization. And times passes on, it is very difficult to incorporate increase the more number of transistors in a single chip. So we already reached that limit. So researchers are trying to find out several options and looking beyond the Moore's law and what could be done beyond that point. So there are several options coming out. One is the photonic integrated circuits or the neuromorphic computing or the qubit based quantum devices. So for photonic integrated circuits, they try to replace the interconnectors, like electrical interconnectors are one of the, it's take a large area in the IC designing. So if you can replace the interconnectors, then you can actually speed the devices because light is faster than the electron movement. And another important point that electronic interconnector causes the heat. This is the Joule heating at that when they the metal contact with the semiconductor junctions. But if you use some optical signals from to pass the signal from one point to another point, you actually neglect this Joule heating problem, and also you can get a faster device. But still the problem is not solved because the device itself, the device footprint is not decreasing. So there is another approach that like all the architecture till now for the electronics or photonic circuit is based on von Neumann architectures, where the memory units and the processing units are physically separated. So let's say for a photonic circuit, you have a optical signals. Then you need a sensor like a photodetector. Then this photodetector send the signal. Just take me the laser pointer. It will be, yeah. So if you see in this image, so the optical sensor sends the signal to the CPU for the logic operation. Then it restores the logic bits in the memory unit. And again, there is a lot like a data operations. So it's fetching data, it's sending data to the memory unit, fetching to the again at the CPU. Then after final processing, it's sent to the output. So it is a continuous sequential process. So during this point, there is a lot of energy consumptions are happened. This is not good for the current days devices, and the footprint of the devices is large for the single operation. So the idea is, if you can integrate this memory unit itself inside the CPU unit, and this single unit can detect the light and process the information for the next step, then it will be beneficial. So it will be one concept for the neural network, like artificial neural network, but it is more on the retinomorphic purpose, like a robotic eye or healthcare monitoring, something like this. So first advantage is that you can access the parallel processing, and massive data can be processed in a smaller time scale. You can do a lot of programming depending on the spike times of the input signal. It might be optically or electrically. So this is nothing but mimicking the biological functions, which we have the neuron-based functionalities. So in these cases, if you take this is, for example, it could be a 2-terminal or 3-terminal. Let's say it's a 3-terminal devices. So in source and drain, you have a signals to read for the reading at the output, and at the gate terminal, this is your control terminal. So by this way, you can write or you can control your devices. Also, as this type of device is generally optically active, so light can be used as a virtual gate or the floating gate to control the device furthermore. So you have a more selectivity on the output. And this is like a 2 neuron input and 1 neuron output functionalities, and depending their durations and their periodicity of these 2 signal, you can actually get it's called a pair pulse functionality or PPF functionality. You can get a different range of plasticity. So, and there are some examples on the 2D heterostructure or 2D based optical RAM. So optical RAM is like a difference of photodetector and optical RAM is like this. So if you shine with light, it like a conductivity is increased. So you have a new state, but after switching off, the current is not goes back to an initial state. If it is a photodetector, then generally the current goes to at the initial state, but you have the current at your output after switching off the light. So this is basically the optical RAM, like how you can actually characterize the optical RAM. So there are several examples using the WSC to HBN or MOS to PZT. Like a PZT is a ferroelectric material for optically writing or electrically erasing functionalities can be done. So, but we are interested using the ferroelectrics 2D material. So why? First of all, what is the 2D? What is the ferroelectrics? Like if you have applied some electric field, the electrical dipoles, like ferroelectrics have dipoles. Electrical dipoles are aligned in certain direction. Let's say in these directions. So if you increase the strength of the electric field, it saturates after a certain time. It's the saturation polarization. And if you start to decreasing your electric field, and if you just reach your initial condition where is no electric field is applied, you have a still inbuilt ferroelectric field due to this ferroelectric dipole, because all the still few dipoles are aligned in a certain direction. This is called the Ramonen polarizations. And you need some negative or the opposite polarity electric field to destroy these dipoles. This is your coercive field. So this is above the coercive field, you have the polarization, or if it is a positive coercive field, you have a positive polarization, or if it is beyond the negative coercive field, you have a negative polarization. So using this ferroelectric, inbuilt ferroelectric field, you can actually have different order of optical signals. Like in this example, you see for this, if the dipoles are aligned, let's say in the left direction, you have a positive photocurrent, and if it is aligned to the right direction, you have a negative photocurrent. So this ferroelectric based devices or this memory star can be categorized in three sections. One is the ferroelectric capacitor. It's basically completely dielectric. During this capacitive phenomena, you have the memory effect, like it's upward polarized or downward polarized. Another section is FTJ. It's a ferroelectric tunnel junctions. You have a very small ferroelectric layer. So if you apply the certain amount of like a high electric field, the tunneling happened after a certain voltage, and you have a very high current at that direction. In opposite direction, there is a huge Schottky barrier formed, and you have almost no current. So you can get a like a high current state and low current state, like a two-state memory devices. And third one is that your FET, which is the ferroelectric field effect transistors. Like I already discussed, you have an extra control, which is through gate. So you have a one channel material, which is basically a semiconductor. And this the gate layer is ferroelectric, and the dipoles inside the ferroelectrics control that the charge or the conductivity of the semiconducting layer. So by this way, you can actually get a different type of memory behavior. So using these 2D materials or 2D material heterostructure based devices, you can actually have a 6 type of devices where all the 2D materials are used. So one is basically simple ferroelectric FET with a ferroelectric FET, where the channel material itself are ferroelectric material. Another is the van der Waal FET, where you have a semiconducting layers coupled with a ferroelectric layer. So the ferroelectric dipole control the conductivity of channel material, and you have a FTG and a ferroelectric diode also. So let's move on. Like 2D ferroelectrics. In 2D ferroelectric, first of all, the ferroelectricity, depending on the crystal structure, it could be the in-plane ferroelectricity or out-of-plane ferroelectricity. Like if you have the ferroelectricity in plane directions, like the left-hand side or right-hand side, it could be assigned as the in-plane ferroelectric material. For example, tin telluride, tin sulfide, or the beta phase indium selenide, like this. If you have the ferroelectric dipoles up direction or the downward directions, you have an out-of-plane ferroelectricity, which is basically the CIPS or MOTE2. And another kind of ferroelectricity is there, where due to the crystal structure asymmetry, the in-plane ferroelectricity as well as out-of-plane ferroelectricity also happen. In this category, there are many theoretically predicted, but only one experimentally demonstrated well, which is the alpha phase indium selenide. So here is 2 crystal structure of indium selenide structure, where you can see basically it's a 5 atomic layer to form a monolayer indium selenide, and due to this like a odd number of atoms, you have either out-of-plane ferroelectricity depending on the middle selenium layer. The red atoms is selenium. So either this selenium atom is close to this up indium or the down indium. So you have a out-of-plane ferroelectricity in that direction. Also, accordingly, you have a in-plane ferroelectricity in this direction. So, and importantly, this ferroelectricity are tangled. So if you control the either in-plane ferroelectricity by the external electric field, automatically the out-of-plane ferroelectricity is flipped. So by this way, you can get a transverse phenomena. So here is an example for the multi-terminal device control. So they applied the they basically form a diode where they apply the, it's a basically two terminal device. So there is no source drain concept. So one electrode, they apply the electric field, another direction, they apply the, negative electric field, and the diode phenomena happen. And another important thing is that this indium selenide is multi-phase, like a beta phase, alpha phase, gamma phase, and they have different metallic property. Like the alpha phase is semiconductor, but the beta phase is metallic. So if you can change the phase from alpha to beta or beta to alpha, you have a different range of conductivity. So you can actually make a phase change memory also using this type of. So how we make the devices? For that purpose, we use the mechanical exfoliated layers. So it's a very like a PDMS assisted exfoliation. First we exfoliate on Scotch tape, then on PDMS. Then we locate what is our suitable layer. Then we transfer that particular layer on our pre-patterned substrate. And this is just example of the indium selenide. And on the silicon surface, silicon oxide surface. And also for fabricating heterostructure, you use the graphene layer. So this is just an example of the graphene. And for the heterojunctions, first we exfoliate independently the indium selenide and the graphene layer. Then you use the target specific pickup to pick this 2D layer from the silicon oxide surface. Then under microscope, and using this CPPA PDMS stamp, like CPPA is for the thermoplastic polymer. So with using the heat, you can actually laminate the 1 2D layer with this layer PDMS stack, and then you can transfer it, and using the high temperature, you can get rid of the layer from the stem to your desired, like a second layer. You can transfer the first layer, then you can transfer the second layer. Finally, using the electron beam lithography to fabricate the devices. This is just a standard process. And these are the examples for the multi-channel FETs, or the one of the vertical graphene ferroelectric heterojunction FET. In the vertical, it's a vertical FET, where the graphene is your channel material and the bottom indium selenide layer used for the ferroelectric layer to control the conductivity in the graphene channel. So these are the prototype of our device prototypes and our setup, where we using this setup we are using for the Kelvin probe measurement. So this is our pre-patterned chip. We use this chip. These big pads are basically fabricated by photolithography beforehand. Then we transfer our layers onto this pad, and then we do the electron beam lithography. Then after finishing the device fabrication, we mount our chip on this PCB board, and we wire bond it. You can see here the bonded wire to the bond pad to the PCB board. Then we mount this PCB board to our AFM setup, which is basically inside a glove box to avoid the atmospheric degradations of the 2D material. And using this, you can see this circular area. There is our electrical connectors, which is connected through the SPA from the outside. By this way, actually, we apply the electric field through the source drain and also the gate terminal, and we can measure the life potential of the devices. So let's directly jump to our result. So before going to our Kelvin probe result, I just want to mention that people generally use this piezoelectric force microscopy, or PFM, to detect this phase, like it's a out of plane phase or in plane phase, or which directions the dipoles are aligned. But it also possible to detect using this potential to detect the phase. Like if it is a ferroelectric material, then either the positive charge on the top surface or the negative charge, depending on the dipolar directions. So either you have a, like if you use the two different set of voltage, So at one case, you will get a higher potential, and the second case, you will probably get a lower potential. By this way, you can differentiate. So this is the same sample, like this is done by different group. They show like a PFM and Kelvin probe material is basically correlated. So you can use either or. But for our case, we cannot use PFM. First of all, PFM is a contact mode material. And if you have a heterojunction and steps in your sample, then the PFM tip destroy your sample. And we have to also apply the live voltage in our FETs. So it will be very difficult to use the PFM for this purpose. So we choose the Kelvin probe for that, for our purpose. So this is just basically a schematic. So this is the FET. We have a source and drain, and we have a gate, and the silicon oxide serves as a gate dielectric. We apply, so when we measure the surface potential between the source and drain, like FET, along the FET channel, we keep grounded the source and drain, and also we apply only through the gate. So these are the surface potential mapping along this channel. You see, for positive to negative gate condition, the surface potential is changing. Like at the positive gate, this side, the source electrode side is more, like the voltage is higher, and for the negative gate, the drain side potential is higher. So if you plot like this, this surface potential versus channel distance for different gate, you see the source side is always 0, but there is a flip in the slope. So for it's flip from positive to the negative slope. So what does it mean? So it means that actually the electric field. So you can calculate the electric field from here. Electric field is nothing but minus of dV dx, where V is the surface potential. For to avoid any ambiguity in our result, so we take the surface potential slope at the middle of the channel, also to avoid any electrode effect is there or not. So from this, we calculate the in-plane electric field, because we are mapping in-plane directions. And we see the in-plane ferroelectric field is changed from positive to negative. So the polarity of electric field is changed. That means the dipole is changing from one side to another side. So by this way, we also tested, like one of the conventional way to say it is a ferroelectric material or not is to check the hysteresis loop. So we started from the positive gate, from 0 to go to the negative gate, and go to the again to the positive gate and come back to the negative gate. We see a clear hysteresis loop. And also we see a remnant polarizations after using different pulse and watch for a few times. We see almost equal amplitude of electric field is happen for positive and negative condition. Then we move to the heterojunction devices. For the heterojunction, we use the laser lithography. Like after fabricating the devices, we put the PCB board under our laser systems to expose half of the channel. So these are just the characterizations of this basic characterizations, what is happening. So we saw this exposed part is converted to the indium oxide. And this you can also correlate with the electronic characteristics. Like here, we do a different intensities laser irradiations for make a different square boxes, and then find out what is the potential difference in the pristine and oxide, and what is the optimum power is required to convert this indium selenide to indium oxide. From the TEM study, we saw that, and the EDS method, we saw we required almost a 90 to 100 milliwatt per microwatt square to convert it from indium selenide to oxide. And similarly, also we found for surface potential is changing and saturate beyond 100 milliwatt per microwatt square. So it almost equal. So you can say that surface potential mapping is also indication to how the property is changing from one to another. And also we can design any type of images to convert it into this map. So the process is quite flexible. And then quickly we go to the our same measurement and find out what is the conductivity also, not only the electric field. So the local conductivity is just like a 4-proof method. You can get the local conductivity by using this formula, and you already calculate the electric field, and you know for a small applied voltage, you know what is the current density, so you get the conductivity. And we see the conductivity is jumps almost 2 order. And for the surface potential mapping, the left one is for the pristine one and the right one is the exposed one. We saw that the surface potential is actually moving from the Schottky junctions to the ohmic junction. And these are also have a similar effect or similar result we found from the our IDVT or output characteristics. So in the left one, you see there is a Schottky junctions behavior, and here is the ohmic junction behavior. Then we also do similar measurements like on our previous case. So we vary the gate bias where we keep the source drain grounded, and we vary the drain bias when we keep the gate is constant. For here, we see there is only the indium selenide part. The slope is changing from positive to negative, but for oxide part, there is almost no change in the slope direction. And in the hysteresis loop, you see also for the indium selenide parts, there is a hysteresis, but there is almost no hysteresis in the electric field for the oxide part. And by this way, actually, you can calculate the barrier height. So in this type of devices, you have a metal to semiconductor barriers. You can get all the barrier information and plot against the gate bias. So by this way, you can actually replicate your band diagram. So if you know what is the conduction band difference for a particular case, you can get the Fermi level positions, and from the band diagram from the literature, you can actually find out what is the conduction band barrier or the built-in potentials you can find out. So after this type of measurement, we just do this optically control memory behavior, and for different type of logic applications. So it is a 2-bit logic applications where we have one input is light, which is either on or off, another input is gate or the electrostatic input. By controlling this these states, you can actually replicate a 2-bit logic operations. We also do the vertical character, like a vertical device. The previous one is the planar junctions. We can do for the vertical function as well, where for the vertical junctions, you have for this case, we use the graphene indium selenide heterojunctions, and these are just using some pulses. So for positive pulses, we saw for both cases, the measurement condition is same. We just use the pulses to rotate the ferroelectric dipole. For positive case, we saw the indium selenide part is lower than the graphene part, that means the band is placed at higher side. And for the negative case, is opposite. From here, we actually plot and find out the barrier between the indium selenide graphene is reversing due to the polarity. And similar way, you can actually replicate the band diagram. So we just saw after fabricating this and after Kelvin probe, I'm not emphasizing this result because we are focusing on this Kelvin probe study and also almost time out. So we just check for the electronic pulse, what is the potentiation and habituation, or different types of characteristics are there. And for optical pulse, we also see different type of optical memory depending on the strength of the input signal. So in conclusion, so we found out how the Kelvin probe can be utilized to detect the ferroelectric behavior or the junction behavior. And that's all. Thank you. If you have any questions, I'm happy to answer.
Thank you. Thank you, Dr. Mukherjee. So because of the time limit, we do not have much, time. So I only select one question. Okay, so the question is as the thickness of exfoliated 2D materials is uncountable, how many devices have you measured and how to guarantee the reliability of the device performance?
Yeah, this is actually a very nice question. And this is the problem with the exfoliated material. You are right that it's very hard to control the device thickness, but we For the graphene, we use only for the monolayer. So it is quite easy to get monolayer or bilayer for graphene. But for indium selenide, it is not really important because we are using this indium selenide for the ferroelectric layer. So if it is, we are using about 20 to 30 nanometer range, like we are not going beyond 30 nanometer or not below 20 nanometer. We found this is a quite good range because at that case, you have a chain of ferroelectric dipoles. So this, like if you have a 2-3 nanometer extra, it is really not a problem. So it's not affect your strength of the dipoles.
Okay, thank you very much for your answer.